move to another problem, B.2, variable size reduction. Another important case for problem size reduction. But this time, the pattern, the reduction pattern is quite different. Variable size, every time the size of the problem reduced can vary. Sometimes larger, sometimes smaller. Yeah. Another interesting case. Yeah. So let's take a look at this case. Yeah. All right. First, let's look at our computing problem number 9, greatest common divisor. Yeah. You are familiar with this problem, okay? Yeah. In your middle school, all students should learn how to find the greatest common divisor of two given positive integers. Yeah. Here, we look at that question another time, but with some higher level understanding. Okay? Yeah. Because in your middle school, you do not know recursive algorithms, right? Nobody knows recursive algorithm in middle school. All right. Yeah. So here, let us use our new viewpoint to understand this question. Given two non-negative integers, here not necessarily positive, we allow m or n to be 0. So two non-negative integers m and n, but not both 0. Now, we do not allow n and m both 0. Why? I will explain later. Okay? Yeah. The reason is quite simple, straightforward. Yeah, but later we will come back to answer this question. Why not both 0? Okay, yeah. Question, find their greatest common divisor, and here we use the function called a GCD function, 2 parameters m comma n. That's the question, how to calculate. Okay, yeah. When we start, here the reference in our textbook. Now, but here I like to go back to the middle school procedure first. In the middle school, how do we find the answer? Yeah, step 1, step by step. Step 1, find the prime factorization of n. Okay, the first integer m. Yeah. Step 2, find the prime factorization of n. Okay, yeah. After that, step 3, find all the common prime factors between m and n. Yeah, by your eye observation. Okay, all right. Then the last step, compute the product of all the common prime factors. Yeah. Actually, each factor has a power of a prime number. Okay, power. Yeah, prime. Yeah. I hope you still remember the meaning of prime. Okay, the prime. Yeah, here. Yeah. Let us just review a little bit. The first prime is 2, not 1. Okay, we do not treat 1 as a prime. 1 is not a prime. Okay, the smallest prime is 2. Yeah, yeah. So its meaning is the only positive divisors it has is 1 and itself. Okay, 1, 2, yeah, only positive divisors. Yeah, we do not count negative divisors. Okay, all right. 3, 1 and 3, you do not have any other positive divisor. Yeah. 4 is not. 4, you have 2. Other than 1 and 4, you have 2 positive divisor, all right? So 5, 7, and so on, okay? Yeah, so the prime numbers, all right. Yeah, so then the prime factorization, assume you know how to do prime factorization, right? Assume, yeah, you know how to do prime factorization, yeah. Later we will talk about this, prime factorization, okay? All right, yeah. So here you can see this method relies on prime factorization, or the main step is the prime factorization. Otherwise, without using prime factorization, you cannot find the answer using, here I talk about this procedure. Yeah, all right, yeah. Let us do a simple example here, GCD of 60 and 24. First, let us do prime factorization. 60 equals 2 squared times 3 times 5. 24 equals 2 cubed times 3. Then let us do observation to get the largest prime, power of prime common factor. Yeah. From 2 squared and 2 cubed, the largest common factor as a power of 2, that's 2 squared. 3 and 3, the largest one, just 3. Then we do multiplication, we get 12. So the answer is 12. That's the middle school procedure. All right. It looks simple, pretty simple. All right. Yeah. Yeah. But the question, prime factorization. All right. So the question is, can you answer this question? How hard is the prime factorization? How hard? Yeah. Here it's not hard, right? Yeah. Here, why here not hard? Because these numbers, we only do prime factorization on small numbers or relatively small numbers. Can you imagine you may need to do prime factorization on large numbers? Think about that. Yeah. Think about. Think about this. You need to do prime factorization on very large integers. Okay. In the middle school, you never need to think about it, right? Because you do not need to do that. Okay. But here, we need to consider this question in the real world now, because in the real world, this is a serious problem. Okay, real world. And people may need to do prime factorization on huge integers. How large? Yeah. Here, when I talk about very large integers, think about how large, right? Because you need to have some idea on how large are these integers. Okay, yeah. Here, let me give you some simple example. How large? 1,000 digits. As an example. One integer, it has 1,000 digits. Think about how large it is. Okay, you can use supercomputer. You're allowed to use supercomputer. Even that, supercomputer. Can you imagine how slow to do the prime factorization in this 1,000 digits? The current technology, based on our impression, the current technology, the computing power is so advanced, right? Now it's the AI era, right? We're already in AI era. So the computing power that we have, I refer to as human, okay? The computing power that we have is huge, right? Yeah. Even that, to do prime factorization for this kind of large numbers. Yeah. Let me use some conservative estimate. Do some conservative estimate. Months, how about that? Yeah. What I mean conservative, I do not say years, all right? So that's why I use months. That's my conservative estimate. Months to get an answer. Now you can imagine how fast it is. The calculation, okay, yeah, supercomputer, okay, and then many supercomputers, okay, but still in the category of several months, not years, not lifetime, yeah, because the old time, the computer technology was not very advanced, yeah, then, years and a lifetime. But now the computer technology already so advanced, but still we need several months computation time. Think about that. So that tells us one thing. This procedure for large integers, not good. Not good for, too slow for large integers. Right? If it's not good for large integers, that means we have to change. We have to find a different algorithm that is fast for large integers, for thousands of digits, even for that large integers. We can get answers immediately. So our question, all right. Yeah, so here, our goal. So here you can imagine the goal we want to have. We want to find GCD of m and n, but both numbers in thousands digits. Okay? Yeah. But we want to get an answer. Get the answer immediately. That's the goal, okay? Get the answer immediately, okay? We do not want to wait several months. So nobody wants to wait several months. So a completely new algorithm is needed to find such lightning fast. So the algorithm is lightning fast. Is that possible? Yes, it's possible. Yeah. Just today, we do not have time to learn that algorithm, but next time we have the time to learn that algorithm, lightning fast algorithm. Okay, yeah. And for this question, actually, I'm thinking about a programming project. Yeah, but because for the programming projects, we may need to do comparisons. Yeah. One, we need to do prime factorization. Another, the sliding fast algorithm to do comparisons. Yeah, but still, I haven't decided. Yeah, still, it's an open question for me. Yeah. So if I give it as an optional project or not. Okay. All right. So